Taking holdout data or cross validation is one of the best way of finding out the original actual error in the more present in the model. As we know, the training error doesn't really give us the original error in the model. We might have overfit or underfit the model. So cross validation error really gives us an idea on the final accuracy of the model, using which we can choose the model complexity and build a better model. So what we do, we take the out of time data or we hold out some data. So out of overall training data, we take, let's say, 80% training data and keep 20% as holdout data, build the model on the 80% of the training data and measure its accuracy on the holdout data, which is 20%. Or you can take 90%, 10%, or even 70-30 is also a good split. So basically, data, we split the data into two parts and then build the model on the first part, consider it as training data, find out the error, training error, and use the holdout data or test data, consider that as a test data, then find out the error on the test data, then finally if on the training data error whatever we got and it is same as that of on the test data, then at least one thing is sure, that we did not overfit the model on the training data. So that is mostly called cross validation or holdout sample data validation, which is one of the most widely used method to find out the real accuracy of the model that we have built. Let us see an example of how data partitioning or data splitting can be done into training data and holdout data, so that we can build the model on the training data and test it on the holdout data. So we have to use caret library. It has a function called create data partition. So we can take the data set and we can choose the probability. So I want to split the whole data set into two parts. First part is 80%, second part is simply 20%. So I'm creating a sample seed by taking 80% of the training data, 5 bits data, and I'm using the sample seed from 5 bits, 80% of the sample data is collected and stored in training data set, and in holdout data set remaining 20% is stored. So I'll try to use this training data, build a model. While building my first model, I'll try to intentionally increase the complexity or increase the complexity of the model and try to grow as big as possible and see the training accuracy. Obviously the training accuracy will be really high. Now the training accuracy is 85%. Now to get a real idea whether this model is really having a power of 95% accuracy or only 5% is error, what we can do is we can do the same. We can create a confusion matrix on the holdout data and find out the accuracy on the holdout data, that is remaining 20% of the data set. So we are using the same model to predict remaining 20% of the data, and we found that accuracy is just 86. Overall accuracy is 95, accuracy on test data is 86. It can't be really that different because these are just two samples from the same data set. So the model is clearly a case of overfitting. So what do? We change the complexity parameters, we adjust them so that we prune the tree a little bit and see the change in the accuracy. Obviously the accuracy of this model will reduce right now because we are not overfitting, we are pruning the tree. So 78% is the accuracy of this training model. And on the holdout data, let us see what is the accuracy. If this is really the true indicator of the final accuracy, then on the holdout data also we should get nearly 78% accuracy, and yes, we got around 78.89% accuracy, and the training data we got 78.9% accuracy. On the test data we got 78.89 accuracy. That is how we can use holdout data to get an idea on the overall accuracy of the model. We have seen an example of cross-validation. We took the overall training data and we took 80% of it, 80% of it, and called it as training data, and remaining 20% is holdout data. Now we did that once, where if we do it 10 times, then it is called tenfold cross validation. Let us see how it is done. So divide the whole data set into 10 parts randomly, use 9 parts as the training data and the 10th part as the holdout data. So we build 10 models, so we repeat this whole process 10 times, build 10 models, find the average error. Now that really gives us the actual training error. So even the smallest error that we are making by choosing the training data 80%, test data 20%, I mean, if there would have been like one small error, even we can reduce that by doing this tenfold cross validation. So how it is done? Let us suppose this is the overall data set. We divide it into 10 parts. While building model 1, we can use all this data as training and remaining this one data set, which is 10% of the overall data, as testing, and find out what is the training error, what is the test error. In the next model, so this is model 1, M1. While building the next model, we will use all these 9 parts except the 9th one. We will use 1 to 8 and the 10th part as the training data, this as the testing data, and build model M2, find the training error and test error, note them down. Similarly, we repeat the same process. In the last step, we will leave out the first one as the holdout data, remaining 9 parts, which is 90% of the data, consider that as the training data and build the model M10 and use it as training data and use the first part as test data, find out the error. So that is how we can do k-fold cross validation, which will have 10 errors. So on an average we can find the overall training error and test error that will give us a solid idea on what is the overall accuracy of the model that we are building. In fact, we can even generalize this to k-fold cross validation. So here we divided the whole data into 10 parts. We can divide the whole data into k parts. I mean, we are generalizing the 10 parts into k equal parts. Keep aside the one of the part, use remaining all parts as the training data and test it on the part that is left out. So if the k value is 10, then it will become 10-fold cross validation. If k value is 5, then 80% of the data will be considered for training, 20% will be considered for testing. So k-fold is just a general version of 10-fold cross validation. So if the k-fold cross validation is the method that we are following, then we will be building k models, and the average error on the holdout sample gives us an idea on the overall testing error. So how do we choose the best model when we are doing this kind of k-fold cross validation or 10-fold cross validation? Okay, choose the model that has least error and least complexity. That means that is simple as well as which is capturing most of the information, or the model with less than average error. On the average there is some error. The model with less than average error but looks simple, that means which has least parameters. So we can finally build a different model using the overall data set with those many parameters. So we can at least get an idea on the overall error and the complexity of the model, and then we can take the overall training data set, use the same complexity and rebuild the model and say that is our final model. So at least we will not be saying that 95% is the accuracy of our model. Every time in this k-fold or 10-fold, every time we are getting an accuracy of 80% only, then we should have a basic idea that our data or our model is good for only 80% of the accuracy, it is not having 95% accuracy. So that gives us a good idea on the overall accuracy as well as the real predictive power of the model. Generally in k-fold cross validation, it's better to choose k between 5 and 10. In fact, 10-fold cross validation is nothing but k equal to 10, which gives 80 to 90% training data, and the rest of the 20 to 10% is the holdout data set.